Hi everyone, Mrs. V here, and today we are going to talk about how atoms get stable using chemical reactions. So let's get on with the whiteboard and start learning. This is the way we've been looking at atoms. We've been looking at their electron structure, and that's going to be really important in describing why atoms take part in chemical reactions. So we're going to be exploring the reasons why atoms would actually take part in chemical reactions. The reason that they take part is they want to get stable. Now, what does stable mean? Stable in chemistry means having really low energy. In fact, all chemical systems tend towards a state of very low energy. So basically, matter or stuff is lazy. If an element doesn't participate in chemical reactions, we pretty much assume that it's already stable. And if we look at our periodic table here, I've got our electron structures here. Where do we find the elements that don't participate in chemical reactions? That's right, we find these in the noble gases. So they're unreactive, and that suggests that they're already stable. So let's have a look from an electron point of view. What is the electron structure of the noble gases? Well, other than helium, we can see that all of them have 8 electrons in the outer shell. The outer shell is also called the valence shell. And these are the electrons in an atom that take part in chemical reactions. So when we look at that, we take a bit of a scientific approach. Of course, helium is an exception because even though it doesn't have 8 electrons in the outer shell is full because the first shell is full with 2 electrons. We take a bit of a science approach. We observe that they are the stable ones. We make a hypothesis that 8 electrons in the outer shell is a stable arrangement, and then we actually look at some evidence. And our evidence is that whenever atoms form ions, they always go to having a noble gas electron configuration. So we figure that it's that 8 electrons that is causing the stability. And 8 electrons, another term for that is the octet. So, and if helium has a duet, but an octet in the valence shell makes things very stable. And we have a rule called the Octet Rule, and this was developed by Gilbert Lewis. Now, Gilbert Lewis, you may not have heard of Gilbert Lewis. Gilbert Lewis was around sort of at the end of the 1800s into the middle of the 1900s. Now, this guy is the one who added information about electrons to the periodic table. He is an extremely intelligent chemist, and he's made a huge contribution. So he's a real chemistry superhero. And his Octet Rule is a theory about chemical bonding. And it says that all atoms tend to prefer having 8 electrons in their outer shell. Okay, so where's my prefer? I lost a bit of my P there. Okay, and that atoms are going to form chemical bonds to be able to get stable in that outer shell, to be able to get that outer shell octet. And they can do that in 2 ways, by gaining or losing electrons, and that means they're making an ionic bond, or they can do it by sharing electrons, and that means they're making what's called a covalent bond. Now, old Gilbert Lewis was nominated 41 times to win a Nobel Prize, but he never got one. That seems a bit strange considering he is our chemistry superhero. But the story goes that early in his career, he worked with some people who were very famous in developing thermochemistry, and one of them is Nernst, and if you study thermochemistry, you'll study the Nernst equation. But he actually criticised Nernst's work publicly, and unfortunately for him, Nernst had a good mate who was on the Nobel Prize committee, and Nernst, I reckon, has made sure that Gilbert Lewis never got a Nobel Prize, and that was to get him back for criticising his work. So it just goes to show you should never publicly criticise scientists' work. Old Gilbert Lewis was actually interesting story. When he died, he was found dead in his laboratory. He'd been working with hydrogen cyanide, and there was, in fact, a suggestion that maybe he'd committed suicide. However, the coroner did find that his death was due to a heart attack. So there goes one of the great dramas of chemistry, all gone. So that's Gilbert Lewis. So always remember Gilbert Lewis, a great chemist. All right, so what do we get out of his octet rule? We get this idea of valence, which is the combining power of an element. So it's how many chemical bonds it needs to make. Now, every time an atom makes a chemical bond, this is going to either add or remove one electron from the valence shell. So pretty much how many electrons are missing or how many electrons you need to lose is the valence. Metals, they tend to lose their valence electrons because most metals have 1, 2, or 3 electrons in the valence shell, and it's just easier for them to lose those electrons. And if we see here the example of sodium, you see sodium's got this 1 electron in the outer shell. Now sodium could go, okay, I need to gain 7 electrons, or I could just lose this 1. And it's just easier to lose it. And what that does is it goes back to the full, or the octet in the valence, in the shell underneath. So having lost its 1 electron, the valence shell is now the next shell down. So now we have an octet in the valence shell. But because it's lost an electron, sodium has 11 protons here and 11 electrons. Over here, because it's lost an electron, it's got 11 protons and only 10 electrons, which means now it has 1 more positively charged particle than negative. So it has a positive charge. So we've formed an ion, which just means a charged atom. Non-metals gain electrons. So if we look at chlorine, chlorine's got 7 electrons in the outer shell, and it's only needing to pick up 1 more to get stable. And so if it gains an electron, so here we're gaining one electron, whoops, go away, 1 electron there. So now it's got 8 electrons in the outer shell, but because now it's gained an extra electron, it has 1 more negative particle than its positives. Because it still has the same number of protons, because the number of protons makes it chlorine, but now it's got 1 extra electron. So overall now this has a negative charge to the chloride ion. So all of this losing and gaining of electrons is one way that atoms can become stable. Now, these electrons don't just, you can't just toss an electron off into the ether, and you can't just grab an electron out of nowhere. So the way this gaining and losing of electrons happens is that metals have to react with non-metals. So if we look at our example we just saw of sodium and chlorine, if sodium wants to lose this electron and chlorine needs to gain it, then by coming together, the sodium can give its electron to the chlorine, and that will make both atoms stable. Now, what this means is both atoms now have charges. So sodium's got a positive charge, chlorine's got a negative charge, and that means they are actually attracted to each other because opposite charges attract. And this is what forms an ionic compound. So if we look over at the diagram here, These green ones are the chlorides and these purpley ones are the sodiums. And you can see the sodiums are shown as smaller than the chlorides, and you can see just looking at the electron shell diagrams here that the sodium atom is slightly smaller, so that's actually true. And they arrange themselves because opposites attract and the light charges repel. They all arrange themselves in this alternating pattern, which is called an ionic lattice. So this is one way of representing this, where we show the dotted lines there are ionic bonds. Often though, you just see the ionic lattice represented in this way, where we just see alternating positives and negatives. So if we're looking at valence is how many electrons we need to lose or gain, if we look at our periodic table, the noble gases, if we imagine the noble gases are sort of here as well, if we're looking at the, this is an octet in the shell underneath, then how many steps away from the noble gases an atom is tells you what its valence is. So fluorine here is only one step away from the noble gases. So its valence is 1. Its valence here is set as -1, but that's because we're looking at ionic valences. You don't have to have a sign, a positive or negative on valence. If we go now to oxygen, so if we look at oxygen here, oxygen is 2 steps away. So its valence is 2. And then if we were to go to nitrogen here, nitrogen is 3 steps away, and so on and so forth. If we come over to the metals, because they're losing electrons, they're going backwards. So if we look at, say, lithium, lithium is 1 step away. It needs to lose 1 electron. Whereas if we were going to look at, say, magnesium, magnesium's 2 steps away. Now, one thing you can't do is this block in the middle, the transition metals. You can't actually, including all of those there, you can't actually work those out. You can't actually work their valences out from the periodic table. They have variable valence, so one atom can have 2 different valences. That's another story. So for metals, you're only going to need to worry about group 1, group 2, and then really just aluminium in group 3. So they're the only ones that you need to worry about working out their valence from the periodic table. All right, so that is how atoms get stable. And I will see you guys in the next video.